Hello everyone, and welcome back to a new episode of Silicon Zeros. In the last episode we did, I think, these two puzzles, Fast 2-2 and Shift 1. Both, in fact, in the ideal amount of time, so that's nice. Were there any more of these that I wanted to dive into at the moment? I'd like to get to branch at some point, but there's no rush. Divide and greater I'm still not really happy to start on just yet. So let's do more stages, or at least look at it. Alright, here we go. You're going to need to get the clock period real low if our processors are going to execute instructions faster than the competition. Bring it down and make it work. Oh, break it down and make it work. Pardon me. So this time limit suggests that we're going to want 3 or 4 stages, roughly-ish. But we'll figure that out when we look at this. So we need memset and addm. That's all we need, right? Okay. And we just have the one writer, so we can't do anything in parallel. It's all about stages. So let's go grab a CPU that we built a while ago that handles these things. Actually, is it just this one? Era CPU? No, this has set R and add R. Set memory. This is just mset. Basic CPU? It says set R and save. I could swear we did something like this. State delay CPU? Set R, add R, and save. It just has 0 mem. Fast 2? Memset and addm. Those are the ones we need. So I think we can just take this and throw a few registers into it. Right? Memset and addm. And it's already down to 29 milliticks, which like, I think just putting another register like right here or here or something is gonna solve the problem. No, not here. More stages. Okay. We only have one writer, but that's fine. It's just we only need one. So let's see. This is the value that we're writing, and the place that we're writing it to. We have to grab as well. Probably this, right? Yeah. So if I run this, it ought to be correct, but too slow, right? Yeah, we're putting values in here. It's all very lovely. Nothing's turning red. But we ran out of time, right? Yeah. Okay. So that should be quite simple to fix. We can just ask this thing, what is our slowest stage? And it's in between the writer and the register, as expected. And so we just have to ask, well, where is the part of that we can... So basically there's... Where can we most efficiently put a register? To cut down the stage the most. We can divide it at any point, and we want the 2 points to be of equal size, ideally. So if we start from here, there's 12 here, 3, 1, 12. And it's going to take us 2 extra cycles in the stage before the register to write to the register, yeah? So if we put it here, this stage will be 14, and this stage will be 16. And if we put it here, this stage will be 17, and this stage... So right here is the best place to put it, I think, just after the readers. Just give me one more register. And we'll need more than 2 slot thingies, so, right? Like, what are we reusing in this writer stage? We're reusing most of this stuff actually is going. This is going to the up here, which will be in the third stage. These two we won't need to carry over, but this we will. So these two and these two need to be carried over. So we need 4 register slots. We'll do this, and then the other things we need are from here. We'll move it this way and this way. I should do it in the other order. This is... wait, what? What did I do? Go back. Unchange the wires. Yeah, so these top 2 are currently being fed up to here. And the bottom one is being fed to here, so actually we need 5. So this top one goes up to the top, so we'll just wire it through here. The second one goes to the second thing. No, wait. Ah, it goes to here and up here. I see. That's why I was confused about whether we would need this one. So we still send it here, but then instead of here... wait, do we need 5? Oh, I changed it to 5, but I hit like escape instead of enter or something. Okay. So, this is fed from here, which we need to change to make it go here. This wire. And last, the memory slot here needs to be carried through as well. And I think that ought to do it. Our timer is lower. And I don't think we could really make it any faster. We could put another register here to save the memory value if we wanted. Wait a minute. This has atoms. Adding another stage here isn't going to work, is it? Because now there's we're going to be... I think we've introduced a problem. We're reading from an address before the previous write has gone through to that address. So I think this won't actually work. Let's see what happens, though. So the first few stages are going to go fine, I think. We're going to write some correct stuff, but I think soon we'll start seeing incorrect values. So we're completed in time, but, okay, so when do we get the first incorrect value? Let's track down and make sure that I correctly understand where that's coming from. Here. So, go back. We're about to write a -5 to memory slot 93. Yep, as a result of these two having a dependency, right? So that kind of stinks. And the way to fix it is not entirely clear. Well, I guess it sort of is clear in broad strokes, but the details, I guess, I don't get. Gonna need some work. I think, anyway. So, the problem is that we start on this instruction here, 5, in order to do that, we read from 93, right? But 93 has not yet had its write from instruction 4 flushed out. So we get the previous value instead of the current value. And we can't really, like we had a problem like this in a previous thing, I think, and we just made sure that the registers, like, I think it was actually, in fact, this very puzzle, like the thing that we copied, whatever the previous puzzle that we used this solution for, we put the register right here, right before the read, and made sure, I think I probably even tried something very much like this, adding another register here to buffer up, to cut down our time. But you can't. You have to make sure that you read process side effects right, all in a single tick. Otherwise, you risk reading stale data when computing what to write. And so what that means is, if we want to put a register anywhere, it must be before the read stage. But if we do that, say we put it here after decoding the instruction, I mean, we already have. We have this here, right? We have a register that decodes the instruction, or after decoding the instruction, and that's too slow. So we do need a register after the read phase, but we are going to have some cross feedback with the execution we're currently executing and the instruction we previously executed. Just like in... Did we have it in shift 1 maybe? No, but in this, see how this guy, we were doing parallel stuff, we had to check, hey, is the previous instruction that's executing at the same time, is it planning to write any of the values that I need to read? If so, I would like to use that value instead. These were executing in parallel. Here, we're going to have to do something basically the same, but instead of talking to the other CPU, we're going to have to talk to values saved in this register? I'm not sure exactly. I think that what we're going to have to do is, when we are going to write something, let's see. So this value that we're going to write, we need to read that. There's two things we could do. One, we could save the arguments that we passed to this writer into this register. Sorry, that's not the right way to say it. We could say, when we're writing this thing, we're also computing what the next write will be, right? And we would therefore ask, hey, what did you write? And use that as a selector to either read the memory address or the thing that was written, right? So that's one thing we could do, is we could compute before we store into this register the correct values with two selectors here. And I guess there's no other option, is there? Well, the other thing we could do, I think, is have them be arguments to this adder, right? save the two addresses, or the one address that was written, and the value that was written to it in this register at the same time. No. Because then isn't it too late? No, it's not. It's fine. We can write to our register at the same time as we save. And then have selectors on this end that for each of these two values check if they should use the actual value in the register or the value in a different register. Now, which of those is a better thing to do? I think it is both conceptually simpler and faster to put it on this side of the register. Because this side of the register just has 12 plus 2 delay, right? Whereas this side has 12 plus 4 delay. So making this longer is more expensive. That's what I think. And I think that really is the only possible solution. So it's just a question of implementing it correctly. Which I believe we can do. So, what do we need to do? How many more things do we need to save in this register? This is getting to be quite a complicated register. In fact, it's too large. We need to store... No, it's not too large. I was thinking we needed to store 4 more things, but we only need to store 2 more. The address we wrote to and what we wrote to it. And then we put some more comparators on this side, checking that against both of the addition arguments. Okay, so let's just scoot this over a bit. I can't, like, name the inputs, can I? No, that would be kind of nice. So give me 7 of these, please. And interesting. The input to this is actually this register itself, and it feels a little silly, but I think what we have to do is send this register its output 4 into its input 5. I guess there's nothing special about that, it just feels a little bit weird to have a register feed itself. It's not an infinite loop, because we're not sending 4 into 4 or anything silly like that. And the value that we wrote goes here. Well, so much for scooting it right, I guess that didn't really help much. Now what we need to do is look at these guys, right? Oh, butts. We can't do it over here, can we? Because we don't have access anymore to the addresses that these values came from. We could store those, but that's too much space in the register. Also, that's what I said I wanted to do anyway, is compute it before. So I don't know, I started doing the other thing instead. So I think we actually don't need these 7 at all, we still just need 5. And it's just that the output from each of these is going to have to go through a selector to decide whether we save it or this. Right? So we have adder, no, not adder. We have equals is what we need, and input selectors. We need both of those things, and that's all. So let's just scooch this over to the side for now, so there's plenty of room to work with. So first, let's test for equality. The value going to here. Sorry, where is this coming from? It's coming from here. Ah, because that's where we actually write. But it's being fed from here, which is what we need to look at. Okay. So check whether the address we're planning to write to, or rather, Yes. No? Shoot. Let's see. I guess, okay, we do want to look here. Whether the address we are writing to in this phase, this is this one, is equal to the address we're reading from for the next phase, which is here. And then if they're the same, we need to get an output selector. No, an input selector. I'm always doing this. Input selector. If those are the same, then take the value that we are writing and feed that instead. Otherwise, this first thing, like so, right? And then we can just copy this, paste it, and get the wiring right. So this, hang on, am I looking at source? Is that right? Yeah, okay, so this is the source address. Yeah, the address we're reading from, and this is the other address we're reading from. So we need to look at this and say, is it equal to the address? Actually, yeah. Is it equal to the address we're about to write to? If so, that's a 1. Then send this value. Otherwise, send this value. And the place that we're putting it is here. Right? I think that's the necessary fix. And has it actually changed our... Wasn't it 19 already? So I think that this hasn't changed our tick speed at all. That's nice. Okay, well, is it correct at all, perhaps? So what are we doing after 1 tick? I guess I can zoom in on this. We're just storing an instruction. That makes sense. Oh, no, stop. Go back, go back. I just wanted to do this. Okay, so let's see. What is this comparator telling me? -4. -4? Oh, it's the value. Oh, no! Wait. Oh, so we only need to do this if the previous instruction was an add m? Actually... Wait. If the current instruction is an add m. But if the current instruction is an m set whose source happens to be a number which represents the same memory slot as the previous thing wrote to, we shouldn't do this operation. So this seems like an edge case that I didn't think of and that we definitely have implemented incorrectly. But I'm interested to see if there are any tests that would catch this, because it's the kind of thing that might not come up if the tests are generated randomly. I think that this is probably something the pleasing fungus would have tested for explicitly, but we'll see. Okay, so -4, very exciting. So we're saving an M set? As our operation selector, okay. And these two inputs are not yet anything, right? Huh. So we're sending a -4 to what to write, and a 68 to where to write it. So that comes out correct anyway. And these equal 1. I don't know if that's interesting. Nothing is equal to nothing. That worries me. Because it means that the next input is going to use this output instead of the memory value, which is like clearly wrong. Okay, well, let's see how bad it looks. Everything is white so far, that's good. That one's wrong. Nope, no, it's right. It was just briefly wrong. Wait a minute! There was at least one bug, right? I think there were 2. This makes me very uncomfortable. Okay, let's see what Carol has to say. Great, we're having forgotten apostrophe. Should be having. Carol loves apostrophes. A lot of trouble with the labor these days. They're demanding above minimum wage salaries, overtime pay, safety regs, all that bull. It's nice to have something going right. I haven't forgotten about that raise, if you were worrying. Things have been messy, but I'll get it all sorted soon. Why are there stars or pluses? What? I don't understand. Do previous ones have that? And I'd like, there was a recent update or something? Yes. Why? What about this? Actually, this doesn't even have that question. What about multiply? This does, but only under ideal. What? What does this mean? Why doesn't it tell me when I mouse over it? Oh, is that like supposed to be a star? Like, hooray, you did it in a perfect amount of time? Modules or something? We'll select. Let's look at... Dragging doesn't even have anything. There's CPU. We did it in an ideal thing. Yeah, I think that this means you have achieved a perfect score. And that must be a recent update, because I'm pretty sure it wasn't doing that earlier. Huh. Well, okay. So anyway, like I said, I think there are 2 bugs in this solution. And I don't know whether they're intentionally excluded from the test cases or if they just don't show up, because they do seem like they should be pretty rare. And you might choose to leave them out and say, we aren't going to worry about that. But I think that, like, we saw... Start over. Step 1. We had this problem where nothing is equal to nothing, right? Which obviously is true, but it means, first of all, actually I guess it's probably fine in this like early instruction step phase thing before we've filled up all our buffers and stuff, but like here we're computing that we didn't write anywhere, and the previous instruction didn't ask us to write, or it didn't use its target register. The previous instruction was a memset. Which means what exactly? It means that instead of using this memory address... Oh wait, actually that's fine, isn't it? I think? Because this only compares equal to nil when target is empty. And that only happens when we're not reading from this anyway, so it doesn't matter which of these two nils we feed. They're both nil. It doesn't matter. Well, no, because this one might not be nil, right? This could actually be a legal value that we wrote in the previous, or that we're finally getting around to flushing. So we could accidentally dump some incorrect value here, right? But that's only in the case of a mem set. If the instruction we're saving here is a mem set, and if the instruction we're dumping here is a mem set, then it's never going to look at this anyway, because mem sets don't look at their target. So that's alright. That was one bug that I thought might exist, and I'm now convinced that it's fine, even though it surprised me. But there was another one, right? Which was, what happens if you run a mem set whose immediate argument is also, by happenstance, the memory slot that the previous instruction... Wait. Running a memory set whose previous instruction doesn't even matter, right? It's an add m. So maybe that's fine, because an add m always... its source and target are actually addresses. Okay, right. So the problem would be if you ran a mem set on, say, instruction 0, well, call it instruction 5, because we want there to be stuff in memory. We run an instruction mem set on instruction 5, and say it writes to register to memory slot 4, right? And then on the next instruction we run an m set whose argument is 4. The value it's supposed to write is 4. That goes here, right? But we compare this against the value we last wrote, or the place we last wrote to. And so if it so happens that we wrote to address 4 with a mem set, or indeed with an add m, and our next instruction is to use an m set to write the value 4 into some other register, then we have a problem, because instead of the value 4, we'll write whatever we happen to write to address 4. So I believe we could fix that with an op selector somewhere, like here maybe, that says whether to use this value or just what came from here directly. It turns out that this doesn't occur in any of the test cases, and I wonder if that's on purpose or not. But I think this is not, strictly speaking, a 100% correct solution to the problem. There's this little error with getting memory addresses confused with immediate values that comes up in between two instructions in sequence. So, okay, well, whatever. We got away with it. We got it perfect, even though it's not actually the right answer. I think that's good enough for me for now, and Pleasing Fungus is watching these videos, so you know, if he wants to fix it, I suppose he will. And that was plenty of time for this episode. Thanks for watching, and I'll see you next time.